your book calls them decision trees. I call them tree diagrams. I've always heard them called tree diagrams. So you might hear me reference tree diagrams. Decision trees, same thing. Okay? And they look like this. Now, when you're done with the decision tree, you should have all possible scenarios. All possible scenarios in your sample space. And there are two. We start with people who go into the store. Yes, the people who went in the store. And I want to follow exactly with the book. So, plan to purchase. They planned or they did not plan. Okay? Now, we know that here, we know 250 people out of 1,000 planned to purchase a TV. We know that 750 people out of 1,000 did not plan to purchase a TV. Okay? I hope you can read that. Now, of the people who planned, and I would just do Y for making sure I'm going to follow your book. I'm going to say Y, yes, they did purchase, or no, they did not. And so 200 people out of 250 people did purchase, and 50 people out of 200 did not purchase a television. Who did plan, okay? Now, if they did not plan, we know that 100, that means, again, yes and no. We know 100 people out of that 750 purchased when they didn't expect to. We call that impulse buying. And we know that 650 people out of 750 did not purchase a television. Okay? And so this is our breakdown. And these are all possible scenarios. You planned to and you did. You planned to and you didn't. You didn't plan to, but yet you did. Or you didn't plan to and yet you didn't. And the nice thing about that, you hear me saying you planned to and you did. Well, you remember that and you can multiply these probabilities together. You can multiply the probabilities together and you can get your total probability. You hear me saying that planned and bought. Planned and did not buy. So what you can do, you can actually multiply 250 over 1,000 times 200 over 250. So let me simplify that and say 0.25 times 0.8 and you get equals 0.2. Now if you look in your book, they broke that down 200 people out of 1,000. What you notice is that's the same as 0.2. And again, you can do the same for plan and did not buy. You can do did not plan and did buy, and did not plan and did not buy. So you can do these multiplications all the way down, and this is what you call a tree diagram. Sometimes this helps us break up the sample space so that we can find all possible scenarios. For those of you who are visual like me, they help out quite a bit. They help out quite a bit. And again, you can follow along in example 4.7, looking at DVRs and televisions. This time, purchase a plasma, 80 out of 300, purchase a DVR, did not purchase a DVR, did not purchase a plasma, purchase a DVR, did not purchase a DVR. Same kind of thing, and you can work through your probabilities. So, the next concept we're going to talk about is statistical independence. Statistical independence. Independence, two things that are not related. This is the generic definition of independence. If you want to think about it, having a child be a boy, so if you're having a baby, the probability it's a boy and the probability that it's a sunny day, they're independent. They don't affect each other. But the probability that you have a busy day at work and the probability that you're cranky at home, these do affect each other. If you're busy at work, it might affect the fact that you could be cranky at home. So those two are not independent, okay? How we write this is the probability of A given B equals the probability of A. So the probability of a boy given sunny day is still just the same probability of a boy. Okay, of having a boy. So the two don't affect each other. Now, this breaks down to what I was talking about, probability of a head and the probability of a 3 on a dice, back from our earlier example. Head and 3 are independent. Getting a head and getting a 3 have nothing to do with each other, and this is why we can multiply these probabilities together. Okay? Because the probability of head and the probability of getting a 3 on a dice are, in fact, independent. Okay? If they were not independent, we'd have a conditional probability on our hands, and we would have to account for that. But that's the multiplication rule for independent events. Page 163 brings us back to where I was in the beginning. Now, that's as far as I want to take us in probability. We are going to skip through the Bayes theorem. Not that I don't think it's important. You are more than welcome to read it, grasp it, get your head wrapped around it. But as we move forward, and what you're going to do in statistics does not depend, the Bayes theorem is not dependent on what you're going to do. So I am going to say that you can skip page 166 to page 171. You can just cut that out of your reading. Okay? So we have some homework coming out of this chapter. 416, 417, 424 I want you to take particular note of. And again, that's carried forward. The same idea of a problem is carried forward into 453. Now, these two problems deal with the fact that you're given undergraduate degree and graduate students were given the same market hedge fund, the exact same, only with different entry fees. Okay, one being very cheap to buy into the same hedge fund as one being very expensive. And the MBA students, they were looking at whether they purchased the expensive one or the cheap one. Since they were identical, and to be able to evaluate the returns, you would expect that an MBA student would be better at that than an undergraduate student, and to see what they did. So that's 424 and 453. 416 and 417, they're the same. Again, you can check the back of the book of reference for some solutions. Now, congratulations. When you finish this video, you are almost halfway done with your statistics class. Most of you, I think, will be happy to hear that, but I want to encourage you to keep going. One good test is not enough. Keep up the hard work. We'll have a test again soon after Chapter 6, and then we'll move forward to the end of the class. So have a great day. Thanks so much.